Hi guys, am I audible? Hi guys, am I audible? Okay, great. So this is the PCD for Leetcode's weekly contest. Weekly contest 448, I guess. Yeah, 448. And in this PCD, we will discuss the first three problems. The fourth problem is, I think, on the level of 6-star coders. So I think the ones who would be up solving that problem does not really need an editorial. And I could not solve the problem during the contest. So even if I had solved the problem for PCD, the explanation would not have been as good as the editorials. So that's why we are going to discuss only three problems. Like in case if you are thinking why are we not discussing the fourth problem, it's because first of all I did not solve the problem on my own, so I can't really explain it that well. Nextly, if there is someone who is interested in solving the fourth problem, then he would be at least skilled enough to absolve it from the text editorials. In case if um, a person is not having that habit, then probably he won't be able to understand the fourth problem anyways. Okay, so before starting the PCD, let's discuss about TLE Eliminators CP31 sheet. So this is a CP31 sheet provided by TLE Eliminators. So what it has is it is having problems of difficulties from 800 to 1900. For every difficulty, there are 31 problems handpicked by Priyansh or some um TL Eliminators coders. So even if the problem is picked up by some mentor of TLE, it is still approved by Priyansh himself. So it's sort of like a guarantee from Priyansh that the problems would be good enough for practicing. And this is a sheet that you can definitely check out. So let's begin the PCD. So the first problem of the contest is maximum product of two digits. In the problem, we are being told that we have been given an integer n and we have to return the maximum product of any two digits in n. And in case if a number is having the same digit come more than once, then you can use both of the digits same also. So if a number is like 22, you can take both the digits as 2 also. Um, yeah, so the problem is like very straightforward. You would be given a number, let's say like 1, 2, 4, 3, 4, 1, 7, any number. What you have to do is from this decimal representation of this number, choose any two digits of your choice. Let's say I choose this 4 and this 4 and take the product of these two numbers. It would be like 4 into 4 equal to 16 here. What we want to do is we want to maximize this product. So problem is like you have to take an integer n, like you would be given this integer n as a parameter of the function. Choose two digits of the number n. After that, take the product, like basically find the product of the numbers, if the of the two digits. And what we want to do is we want to maximize this product, right? This is the problem. So one thing that should be pretty obvious right now is, since we want to maximize the product and we can choose any two digits of our choice, what we would want to do is we would like to choose the largest two digits, right? We would want to do something like this. So in this case, the largest two digits are 7 and 4. So you can take any one of these fours. So guys, is it making sense? Probably everyone would have solved it. So um, maybe this might be the reason why nobody would comment anything. So yeah, for now, all we want to do is just find the two largest digits and pick them and find their product. So how will you find the two largest digits of a number? I will share different ways. One easy way for doing this is, whatever number you have, let's say I had the number 1, 2, 3, 4, 5. I can use, like if I'm coding in C++, I can use the toString function on of this number, which will convert this number into a string, right? Right now this number was already sorted, but if the number was something like 1, 2, 4, 1, 5 or anything, I will get the digits of the number in form of a string. Now, once I get it in a form of a string, I can just sort this string so that it becomes something like 1, 2, 3, 4, 5, or sort it in a way like 5 comes at the beginning. You can either sort it like this or you can sort it like this, as as per your choice. And once you have done it, the largest two digits would be at the back of the string. So you will be able to find the two largest digits in a very easy way. The code would be very short. First line would be to just convert the string, convert the number into a string. Second line would be to sort the string. And in the third line, you would have already got the two largest digits. This is one way you could have done. Another way in which you can find out the digits of a number is, um, this is also a very common way, a very standard way. What we do is, um, we just find out the last digit by saying something like n mod 10. है ना? Whenever you want to find out the last digit, you can always say n mod 10. Now, obviously, if you wanted to find out the last two digits, you could have done something like n mod 100. If you wanted to find out the last three digits, you could have done something like n mod 1000. Generally, when we want to find out the last digit, we just do this thing. So in this way, you can find out what is the last digit. You can store it in some array or something as per your choice. And then you can divide the number by 10. When you divide a number by 10, what will happen is, if the number was 12415, it will become 1241. Because if you do something like 13 by 4, I believe you guys know that you would get something like, even though 13 by 4 is 3.25, in C++ and in most of the programming languages, you will just get 3. And whatever was coming after this decimal would get erased because we are having the int data type by default. So with the same idea, we can just remove the last digit by saying n by 10. And then we can just keep on doing it until, like, as long as n is greater than 0. Just keep on finding the last digit, store it in some array or something, and then divide by 10 to remove it. Again, store the last digit and divide by 10, then store the last digit, then again divide by 10, store the last digit, then again divide by 10. At some point of time, the number will become 0 and you don't have to do anything. And I just told you about the two most common ways for finding out the digits of the number. Um, Most of the times people do this thing because the code of this is also not too big. And alternatively, if you want, you can just go with this technique also, because the code here is also pretty short. Internally, what will happen is internally, the function will also do this thing for converting the number into a string. It will just make our code shorter, but um, the time complexity and everything would be pretty much the same. So once we would have stored here, like here, once we would have stored the uh, digits of the number in an array, we can just either we can iterate over it twice to find out the two largest digits, or you can sort it to get the two largest digits at the end of the array. Um, 1, 1, 2, 4, 5. So the two largest digits will get at the end of the array. And we can just take the product. We don't really need to do anything else. Can you please explain question 3 before question 2? No, actually, we will go in order. And the reason I did spend a lot of time at the first problem is because if someone is watching the PCD for the first problem, probably he needs this much description for the problem. Otherwise, he would have already been able to solve it now. So the code for the first problem is like this. You can create a vector in which you will store all the digits and do the method that I have discussed here, the second one. The second method here for finding all the digits of the number, and we have stored them inside a vector. Then I sorted the vector in the decreasing order or non-increasing order. So the largest digits would be at the beginning. So digits 0 into digits 1 would give me the two largest digits, or basically the product of the two largest digits. And by the way, the time complexity here would be um, the time complexity for both of these methods would be the go of log 10 of n. Please see, it is log of 10. Log 10. Like generally we say log n. Whenever we have log n, most of the times the base is 2, but here the base is 10. So it is even faster than log base 2n. So let's move on to the second problem. The second problem is fill a grid, fill a special grid. We are being given a non-negative integer n representing a grid of size 2 raised to the power n into 2 raised to the power n. You must fill the grid with integers from 0 to 2 raised to the power n minus 1, 2 raised to the power 2n minus 1 to make it special. A grid, a grid is special if it satisfies all the conditions. All the numbers in the top right quadrant are smaller than those in the bottom right quadrant. All the numbers in the bottom right quadrant are smaller than the numbers in the bottom left quadrant. And all the numbers in the bottom left quadrant are smaller than the numbers in the top left quadrant. And each of the quadrant is also a special grid. We have to return the special 2 raised to the power n into 2 raised to the power n grid. And any grid with just one element is special. So in simple words, in simple words, if you have, let's say, a 4 by 4 grid for now, then this grid is special if you have this first quadrant, like these are the 4 quadrants here. So first of all the quadrants should be special in themselves. So all the quadrants should be special. Nextly, all the elements of this quadrant, the top right quadrant, should be, let's name the quadrants first. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4 itself. So all the elements of this second quadrant should be smaller than the elements of the fourth quadrant. all of these should be smaller than the elements of the quadrant 3, and all of the elements of quadrant 3 should be smaller than the elements of quadrant 1. So if you, let's say, have a 4 by 4 grid, if let's say you had to create a 4 by 4 grid, then what you want to do is you want to have the smallest elements in this quadrant, है ना? Because even the largest element of this quadrant should be smaller than the elements of this quadrant, right? So to make a special grid, what you would want to do is you would want to fill this quadrant first, then this quadrant, then this quadrant, then this quadrant in the increasing order, right? You would have something like this in a grid if it is special. Does it make sense? In the problem, what will happen is you will have to create a 2 raised to the power n into 2 raised to the power n grid, having elements from 0 to 2 raised to the power 2n minus 1. Please notice that if you have a grid of x into x length, then the total number of elements is 2 x raised to the power 2. So here, since you have 2 raised to the power n into 2 raised to the power n grid, the total number of elements would be 2 raised to the power n square, that is 2 raised to the power 2n. So this is why in the problem they have asked us to fill elements from 0 to 2 raised to the power 2n minus 1. Because this thing, like these are totally 2 raised to the power 2n number of elements in total. Right. So input for the problem would be just this n. Output would be the complete grid. Guys, please tell me if it is clear or not. For solving this question, do we need to know DP? No, you don't need to do. You don't need to know about DP for the solve for this problem. And the constraints here are pretty small for n. So here n is less than equal to 10. Since we have to create a 2 raised to the power n into 2 raised to the power n grid, here 2 raised to the power n would be something like 2 raised to the power 10 is pretty much like 10 raised to the power 3, because 2 raised to the power 10 is actually 1024, which is almost 1000. So the total number of elements in the grid would be somewhere around 10 raised to the power 6. So we can have the 2 raised to the power n into 2 raised to the power n time complexity with these. Even a little worse than that would still be fine. Right. Okay. So let's talk about the solution part. Like, how would we solve the problem? So the first idea is, like, the main idea here is, if you think about a grid, let's say the complete grid, which is having some size, let's say n, initially n would be equal to 2 raised to the power n. There is a, let's say, n by n grid, and you want to fill elements in this grid from 0 to n square minus 1, and you want to make sure that the largest element of this grid is still smaller than the smallest element of the next grid. So can I say, um, I had these n square elements, let's say elements from um, 0 to 15 here. Can I say that I can just make 4 parts of these elements? Basically 0 to 3, or maybe let me write it like this. You have 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Right. You have these 16 elements. Right. So can I say that if I put up the smallest 4 elements in the second quadrant, then the next 4 elements in the fourth quadrant, then the next 4 elements in the third quadrant, and the remaining 4 elements in the first quadrant, then at the very least, the condition of having all elements of the second quadrant smaller than all elements of the fourth quadrant would be satisfied, along with the next condition of all elements of 4 being smaller than all elements of third quadrant, and all of those elements being smaller than the first quadrant. All of these conditions would be satisfied at the same time, right? I had I had two conditions, I guess, for having a special grid. One condition was that all the quadrants should be smaller. Another condition was the comparison of the quadrants, that the second quadrant should have all smaller elements than fourth, then third quadrant, then the first quadrant. So I can satisfy all of these conditions, like all of this whole condition, by making sure that I fill second quadrant with all the smaller values, then the fourth quadrant with the next values, then the next four values in this quadrant, then the next four values in this quadrant. This is idea one. Second idea is like to make sure that you have all the quadrants special. What you can do is you wanted to make sure that this is a special quadrant, right? So let's say if you had a function f being called for this whole matrix having these four quadrants, can I say that, hey, I can just use recursion to call the same function for all the four quadrants, that apply the function for the first quadrant, apply the function for the second quadrant, apply the function for the third quadrant, and apply the function for the fourth quadrant. Can I do it? Like if I do this thing, then all of these quadrants would be special for sure. And I can just make sure that I fill the elements in the quadrants in this order to make sure that the condition for like the second condition is also satisfied. So I would be able to satisfy both of these conditions. Does it make sense? It would be a pain to understand your code in the chat right now. I think you can also see the way I'm able to see your code. So I won't be able to debug it for now for you. Um, Maybe I can debug it later if you can share your submission link, which has a cleaner code. Like in the chat section, you don't have any indentation and new lines, no? So it is difficult to code debug there. Okay, so the main idea that we have got so far is you have to create a function. Like we would like to create a function which will take a matrix as input. We will divide it into four quadrants. Then what we will do is we will say that, hey, start filling elements from 0 for the second quadrant. Once you are done with the second quadrant, then you would like to fill the fourth quadrant. Once you are done with the fourth quadrant, you will start filling elements in the third quadrant. Once you are done with the third quadrant, then you will start filling elements in the first quadrant. You know? And when I say fill elements, what I would do is I would keep on applying recursion until like for this subgrid. So for this subgrid, it will also have four quadrants. You know? Those quadrants will also have four quadrants. At some point of time, you will get to subgrid which is having only one element. Basically, it would be a one by one grid. है ना? So in that case, what we can do is we can have two global variables, maybe like grid and the start value, or basically a value. You can have these two global variables. So in this case, in the grid, you would obviously know about the row and column of the one by one grid you have, and you can just fill the value as this value. Yeah. So here you can put up the value we have in the variable with name value, and then you can increment the value. Something like this. I'm not too sure if everyone is able to understand the visualization I'm trying to show or not. Please give me some live feedback regarding this. Like the way in which everyone would have learned about recursion might be different. The way in which I did learn about it, let me tell you about that also. So the way in which I got to learn about recursion was think about the current problem, and if you can break it down into some similar sub problems. Let's say I can break it down into four sub problems. Then just believe that these sub problems will actually give you the correct output. Just believe in it and try to make sure that if they are giving you the correct output, then with the help of these correct outputs, you are creating the correct answer for the current problem. So like in our case, we wanted to make this bigger matrix special. So we did call the same function for these four sub problems, for these four quadrants. And now we will just believe that they will give us the correct um, answer for these quadrants. And now we just need to make sure that if we are having these four quadrants special, then we are forming a special grid. We need to make sure this thing will happen. This thing happens. If we are able to make sure this happens and we have a good base case, like we have a good base case here, that if you have only one element left, then it is special in itself. Then you would be able to form. You would be able to apply recursion properly. So there can be two ways in which people might apply recursion here. One way is for the matrix from which you form four sub problems. You had the matrix here and the four sub problems 2, 4, 3, 1 here. One thing is whenever you call the function, obviously you need to have some parameters for this matrix, maybe like um, the row number, column number, the size of the matrix, row, column, size of the matrix. You will have these things obviously, and along with it, you can keep a variable which will tell the smallest value of this matrix. If if let's say I had to fill elements from 0 to 15 in this matrix, which was having size 4 by 4, then for this matrix, I will tell him that, hey, you have to fill elements from 0 to 3. Then for this matrix, for this quadrant, I will tell that, hey, you have to fill elements from 0, not 0, but 4 to 7. Then for this submatrix, I will tell him that you have to fill elements from 8 to 11. And then I will tell him from 12 to 15. This is one way in which people do apply recursion. Another way in which people apply recursion is just focus on breaking down the problem. Okay, don't worry about the value of the element that you have to put. Just make sure that the uh, quadrant that will have the smallest values, the recursion call for that quadrant is called first. If you are having this logic, then obviously for this quadrant also, the quadrant which the second quadrant, the recursion call for the second quadrant would be called for that as well. Like this quadrant would be a matrix in itself. When the recursive function would be applied here, it will also have four quadrants, and it will also apply the recursive function for the quadrant in which you have to put up the smallest value, and it will happen so that eventually the cell of the complete matrix that should have got the smallest value, recursive function would be called for that um, cell, and there you can just fill in the value. You can have a global value. You can have a global variable with name value, or for now let's call it as val, which would initially be 0. So you will put up the value of this variable val there, and then you will say val plus plus, so that when the next cell would be called, the recursive function for the next cell would be called, you will have a bigger value there, and you will keep on putting the values in that way. So these are two ways in which I think people apply recursion. These are the two ways in which I have seen tutorials for recursion when I was a beginner. Whichever suits you more, you can apply that one. Okay. Yeah, so guys, please tell me if it is okay, or do I need to do some dry run or explain also? Oh, okay, let me do some dry run. Yeah, dry run will actually make a lot of sense in this problem. Okay, so we have a 4 by 4 grid here. Okay. What we will do is, for this grid, you will have um like you want to make it special, so you want the 4 quadrants to be special. So the quadrant which will have the smallest values here is the top right corner, this quadrant 2. So you would like to fill this quadrant first. You would like to fill the quadrant with the values. Um, for the bigger matrix, you had the values from 0 to 15, right? You had the values from 0, 1, 2 till 15. So what we want to do is we want to fill the smallest 4 values in this quadrant here. So a recursive function for this quadrant would be called. Here now for this quadrant, you will have the 4 values 0, 1, 2, 3 that you want to fill in, right? Now, again, recursion would be called. You would say that, hey, fill this quadrant first. So for filling this quadrant, this time we will have only one value that is being passed. Um, I hope you can see the pattern. If you had maybe 16 values in the whole matrix and you had to fill one quadrant, you gave out 4 of the values, the first 4 values for this quadrant. Nextly, from this quadrant, you had 4 values here and you wanted to apply recursive call here. So for this cell, you will give only one value, that is 0. So that would be filled here. This is the base case, right? Similarly, now this is the next cell that should be filled, because you fill this quadrant first, then this quadrant, then this quadrant, then this quadrant. So for this quadrant, now what will happen is you will have um yeah, you have already filled this one value here. So now for this quadrant, you will give the next value, that is 1 here. So 1 would be filled. Then similarly here 2 and here 3 would be filled. Nextly, the recursive call, like the recursive call for this quadrant is done. है ना? This quadrant is done here. So the recursive call for the next quadrant here would be called in the main matrix. So it would look like this. You would have these, you would have to fill 4 values there. Now for this quadrant, you will have the next 4 values, that is 4, 5, 6, and 7. So you want to fill 4, 5, 6, and 7 here. So again, you will just call the recursive function for these one by one. You have the cells of one size, so they would be filled 4, 5, 6, 7. So 4, 5, 6, 7. Nextly, for this matrix, you have the next 4 values, that is 8, 9, 10, and 11 that you want to fill. So you will fill up 8, 9, 10, and 11. Then you will call for this quadrant. Here you have the values 12, 13, 14, and 15. So we'll just fill them up 12, 13, 14, 15. And that's it. So 8, 9, 10, 11, 12, 13, 14, 15. Right. So if you had an even bigger matrix, at the end of the day, the same thing will happen. You will just say that apply recursive function for the top right, then bottom right, then top bottom left, then top left, and keep on filling elements. So I hope this did make sense. And please tell me if the dry run did help or not. For the ones who are watching it after the live stream, who are watching it the in the recorded way, please tell me in the comment section if the dry run did help or not. And for now, let's move on to the code part. So one way of coding it is like this. Um, I created a recursive function with name solve here, in which I'm passing three parameters, that is row, column, and size. Because for any quadrant, if I just tell you about the starting row and starting column, that this is starting row is 1 and the column number is 3, or in zero based indexing you will have row to column 0, and the size of the quadrant is 2, then you can figure out the number of elements you have to put up in this quadrant, and you can figure out the cells that would come in this quadrant. है ना? In fact, this is true for any matrix. If I just tell you about the starting row and column of any matrix and the dimensions of the matrix, then you can figure out sub like which sub matrix are we talking about. So in this case, we will just pass on these three things. Nextly, if you want to pass out the numbers that you have filled in the matrix, if you want, you can just pass on this information as well in the function parameters, or if you want, you can have a global variable for it. It's up to you. I would recommend you to try it out in both ways in case if you are new to recursion, because the more you struggle right now, it might look confusing right now. You might spend a lot of time struggling to understand what is happening. But once you understand this, it will be really good for you. Otherwise, when you will learn about DP or when you would um, learn about trees, you will just get very confused if you don't know about regression properly. So for applying regression, what we have done is the base case is if the size is 1, then we just update grid row call. Like this grid row call will tell you about a cell and you are putting up the value val there, and then we are incrementing the val. So you can call it like this, or if you want, you can just write it like this, because both of them will give the same thing. If you want, you can write it like this also. Nextly, I'm just having the recursive calls. So the top right subgrid, then the bottom right subgrid, then the bottom left subgrid, and then the top left subgrid. That's it. So before calling the function solve, I like did resize the grid. I had created it here. Oops. And once I'm done with finding the grid, I will just return it. Explain code. You did okay. You sent this message 3 minutes ago. Yeah. So we are done with the code also, and the time complexity here. Um. Okay. Time complexity here would be a little tricky to calculate. Let me see how to explain. So see, a recursive function would be called for the n by n matrix one time. Because of this n by n matrix, there will be 4 recursive calls for the matrices with the size n by 2, right? Let's call this as n by 2 for now. Then for the matrices having the size n by 4, there will be 16 recursive calls. Then for size n by 8, there will be 32 recursive calls, right? Eventually, you will have n by 2 raised to the power k, for which you will have um, when k was 0, we had 1. When k was 1, here we were having 4. Yeah. So we will have 4 raised to the power k recursive calls there. And the value of k should be log 2n. Like when this n by 2 raised to the power k become 1, for that case, k would have to be something like log 2n. So the time complexity here should be something like 1 plus basically summation of 4 raised to the power k for k from 0 to um, log to n. Now for 4 raised to the power k, we can call this thing as 2 raised to the power 2k. By the way, guys, I don't know about this earlier. Like I had not calculated this thing during the contest. Whatever I'm doing right now is just in front of you. I'm also calculating to figure out what would be the time complexity. So the overall time complexity should be something like summation of 2 raised to the power 2k for k to go from 0 to log to n. Okay. So it would be like 1 plus 4 plus 16 plus 32 plus so on till 4 raised to the power k. Or you can. Okay, one way to find out the time approximate time complexity is to realize, let's say if you had value of k such that this was the only time complexity. Let's say if k was equal to um sorry, it is not 32, it is 64. Yeah. So let's say if k was equal to 3 here, then in that case the time complexity would be 1 plus 4 plus 16 plus 64. Like this would be the number of iterations. So all of these iterations are actually insignificant in comparison to the last one. है ना? If you have the time complexity as big O of 1 plus 4 raised to the power 1 plus 4 raised to the power 2 plus 4 raised to the power 3 and so on till 4 raised to the power log to n or log to k or whatever, then in that case all of these are actually insignificant in comparison to the last guy. So for overall time complexity, we can just look at the last guy. And as we generally say that if you have something like big O of n plus n square plus n cube, then you only say the time complexity as big O of n cube. Similarly, here if you have big O of 1 plus something which is growing exponentially, you can just look at the last guy. Since just this last guy would obviously be greater than the sum of all of the others. So the overall time complexity is big O of 4 is the power log to n. Log to n would be something like 10 here. So big O of 4 is the power 10. That is nothing but 10 is the power 6. So yeah, the time complexity at the end of the day is um basically this thing is actually n. And in the problem you were being told here this n was nothing but 2 raised to the power n now. So log of 2n would be nothing but n. So overall time complexity is actually 4 raised to the power n. And n is as big as 10. So 4 raised to the power 10 gives you 10 raised to the power 6. Okay, so let me just explain you once what I did for calculating the time complexity. This is something which is not being taught in courses, I guess. I never learned about it during a course. Um, it just comes out by practicing. So you wanted to calculate the time complexity for the recursive function that we have created here. So what I did is I just focused on finding out how many times a recursive function would be called for each matrix. So for the matrices with the size n, basically n by n, there will be only one recursive call, which would be called initially. It will call, it will have 4 recursive calls for matrices with size n by 2, which will have 4 recursive calls for matrices with size n by 4. So for size n by 4, you will have 16 calls here, and then there were 64 here. For the size n by 8, there were 64 calls, and so on. So you can notice here that for n by 2 raised to the power k, the pattern here is for n by 2 raised to the power k, we are having 4 raised to the power k number of calls. And the sum of all of these would eventually be equal to like you can approximate that thing to be equal to 4 raised to the power k. Because if you have something like 1 plus 4 plus 16 plus 64 plus so on, where you are getting things multiplied by 4 every time, you can notice this guy is greater than the sum of the previous three. Similarly, the next guy would be greater than the sum of all of these. Similarly, the next guy would be greater than the sum of all of these, and so on. So eventually, when you reach 4 is the power k minus 1 plus 4 is the power k, this 4 is the power k guy would be greater than all of these. So for approximating the time complexity, for all of these, you can just say it to be somewhat equivalent to this guy. Basically, it would be in the range from 4 is the power k to 2 into 4 is the power k. है ना? And 4 is the power k comes out to be something like 10 is the power 16. So it would be somewhere in the middle of 10 is the power 16 to 2 into 10 is the power 16. Yeah, it will be our time complexity. To be honest, I did not really need to calculate it like so much mathematically in front of you. I could have just told you that it is gonna be pretty much just um, big O of 2 raised to the power n into 2 raised to the power n, as we had discussed at the beginning. I had a very good idea that it would be almost equivalent to that. Not even a log and factor would be there. But still, I calculated it mathematically because I felt that it might be good for some beginners to see. So now let's move on to the third problem. We will cut out the previous part from the recording, so it's not really a problem. Yeah, so this is the C problem. Merge operations for minimum time traversal, travel time. We are being given a straight road of length L, an integer n, an integer k, and two integer arrays position and time of length n. The array position lists the positions of the signs in strictly increasing order. The signs would be available on the straight road. And we have another array, this time. So time I represents the time in minutes required to travel 1 kilometer between position I and position I plus 1. So it's basically like you have a road. The length of the road here is L, starting from 0 till L. There are multiple signs on the road. So there are a total of n signs on the road. We have been given two arrays, position array and the time array. This position array actually tells us about the positions where the signs are present, right? So the first sign is present on this place and the last is present at this place. So pos of 0 would be 0 and pos of n minus 1 would be equal to L. And other than that, the cell signs can be anywhere. This array would be sorted as well. Nextly, we have this time array, which is actually denoting like time I. On the ith sign, you will have the value time I written, which denotes the time required to travel 1 kilometer between position I and position I plus 1. Basically, if you have a sign here, then this is actually telling you about the time you need for every kilometer between these two signboards. So nextly, we have been told that out of these n signs, we have to perform exactly k merge operations on these n signs. In one merge operation, we can choose any two adjacent signs at indices I and I plus 1 with I greater than 0 and I plus 1 less than n. We can, like if we have chosen I and I plus 1, then we will update the sign at index I plus 1 so that its time becomes time I plus time I plus 1, and the sign at the index I would be removed. And we have to return the minimum time, total time travel or travel time in minutes to travel from 0 to L after exactly k merges. Okay, so we have already understood what are the signs and what are the given variables. Now let's understand what is a merge operation. So we have to apply exactly k merge operations on this given row on the signs that we have. So if you have like for one merge operation, what we can do is we can choose two signs I on index I and I plus 1, and when you merge them, what will happen is, if let's say these were the two signs with time I here and time I plus 1 here, then after the merge this one would be removed, this guy would be removed, and for the other sign you have, the new time will be time I plus time I plus 1. So this merge operation can be considered in this way as well, that you choose an index I, remove that sign from there, and add the value of this time I at this position, at the next position, whatever position that we have. And one more thing, out of like for these I and I plus 1 that we had been choosing, um, yeah, wait. I plus 1 is less than n. Yeah, yeah. So this I and I plus 1 that we had chosen, um, I has to be greater than 0 and I plus 1 has to be less than n. So actually, like this is a mistake I had made earlier while telling about the problem earlier. We can actually apply the operation on the last two signs also. In the earlier explanation, I had told that you cannot have the last position taken, but you can actually take it. That was my mistake earlier. So yeah, in general, we can apply operation between any two adjacent signs other than the first one. The first sign cannot be removed, other signs can be. So the other way that we have seen for applying the operation is the merge operation. What we are doing in this is choose some I, um, remove the ith sign, and update the next sign, um, like whatever is the value for the next sign, it would be incremented by time I, right? And we are talking about the um, like right now we are actually talking about time I plus 1 to be removed. Oh, sorry, I plus 1 to be incremented. So this will happen in one merge operation. So is everything good till this point? Uh, Guys, please tell about the problem. Is it good till this point? I will look at the other comments after the problem. Okay, nice. So for solving the problem, um, the first idea that you will probably get is, okay, sorry. The problem is not done here. We have understood what we can do in one operation. What we have to do is we have to apply exactly k operations of this merge type on the given signs, and after that, like we have to apply them in a way that the travel time after all the operations is minimized. Right. This is the problem. Like this is our goal. So we will have to return the minimum possible travel time after exactly key operations in any way. You can apply on anything of your choice. So the first idea that you might get is, since we want to minimize the time, you would like to check for every sign that if you remove this guy, then what will happen? How much time will increase or decrease? So if you remove this, um, if you remove a sign, then what happens is, yeah. So if you remove a sign, then what happens is, for the distance between, basically the road between pause I to pause I plus 1, which you would have earlier traveled in pause I plus 1 minus pause I multiplied by time I. Earlier, you would have traveled this road, this portion of the road with in this much time because of time I. But once you um, apply operation on this guy to remove it and increment the next sign, then in that case, this portion would be traveled in, like, instead of time I, you will have time of the last sign, the last unremoved sign. So if the previous sign is unremoved, then you will have time last used there. Let's say in case if the previous sign is also removed, then you will have some other sign, um, which will tell you about the speed that you can use for this distance, right? So in general, it is very difficult to realize which k signs should be removed. If you try to think greedily, you might decide that, hey, right now, maybe in a road you are having, let's say, 5 signs that you can remove. So you might realize that if you remove this sign, you are saving 5 minutes. If you remove some other sign, you are getting 3 minutes, let's say. But the thing is, once you remove the sign, the amount of time you um, save for the other guy will also change. And now, what will become for this is something you don't know. Like right now, let's say you were saving 5 minutes if you had removed this sign, and you had removed this sign because you were able to save only 3 minutes here. But after removing this guy, you might be able to save like 20 minutes on this guy now, right? And um, let's like um, the point that I want you to notice here is, earlier you were saving something else, but apply when you apply something here, what you were getting on some other place has now changed, and it can change to anything which you can't really decide early. So you might have this kind of an edge case in the current approach, like in the current approach that we have, where we just find out the maximum time we can save by applying operation for every index, and wherever we can save the maximum time, we will apply an operation there. Then we will again see what is the maximum time that we can save on some indices. So this approach will work in a case like this. If let's say you save 1 minute if you remove this sign, and you save 20 minutes, like if you save like 1 minute here right now, if you just remove this guy. But if you remove this guy, then you will save 20 minutes. So removing both of these together will save you 21 minutes of time. Whereas you are getting 2 minutes being saved if you remove this guy. So with our current approach, what will happen is we will remove this guy first, then we will remove this guy. And after removing this guy, we will realize that we would have saved 21 minutes if we had not applied our operation at some other place. So in a nutshell, since all of these things are not really completely um, independent, you can't decide in this way that pick up the one which is giving you the maximum benefit right now, because when you pick something, the benefit you are getting from other places can change significantly. So at least with the obvious approach that we have in our mind for greedy, it is not working, and most probably we have no greedy approach that will work. So the next idea that we always get in our mind is, if greedy doesn't work, then what if we just try out all the possible combinations? In general, for for the road that we have and the signs that we had, if there are n signs, you can basically remove any sign of your choice. Sorry. Yeah, so you can remove any sign of your choice other than the first or the last guy, you know, because we can just choose a pair and the first sign would be removed. So there are 48 signs, or there are 48 indices, out of which you have to choose exactly k, which would be removed. So the total possible combinations that we have here are 48 ck, which is, yeah. So this is just too many. This will give us the correct output. Like if we actually try out all the possible combinations of choosing k signs and we remove them, and then we calculate the travel time, and then we find out the minimum travel time that we have obtained. But um, it will actually take too much time and we will get a TLE. So even though it works for the small test cases, it will fail for the bigger ones. So we have to think about a more optimal one. Since we can't straight away solve the problem by finding all possible combinations via some recursive or backtracking approach, we should think about dynamic programming, right? So for approaching with dynamic, like for thinking about a dynamic programming solution, there are two ways I can think of, like the two ways that people do prefer. One way is they think about a recursive solution and then they try to figure out what is the redundant work they have been doing, like which stuff can be removed. Like in case of a Fibonacci number, yeah, taking as an example, many people prefer in this way that if you have to calculate a Fibonacci number, then write out a recursive approach first, that is f of n is equal to f of n minus 1 plus f of n minus 2. And once you have got this approach, then you figure out the redundant work that you have been doing, है ना? And you just memoize your solution to deal with it. So this is one way. We will talk about this also. Another way that I do prefer, which is actually faster for us, is don't think about the brute force solution. If you have enough practice of dynamic programming, just straight away go and try to think about the dynamic programming solution. So this is the second way, which is actually something I prefer and is faster. And I think mostly high-rated competitive programmers directly think about DP solution and directly write the iterative DP solution also. For the explanation perspective, I will go with the first way, that is thinking about brute force and then optimizing it. But the code that I have written is actually iterative because I had directly written an iterative solution. Anyways, let's begin with the easy approach first. For now, the easy approach is simple. What you would like to do is you would like to iterate from left to right For every sign, you have two possibilities. Either this would be removed or it would not be removed. है ना? Either you will remove it or you will keep it. Right. So we can do something like this, like have a recursive function in which uh, for the first guy, obviously you have only one choice, you have to keep it because you can't remove the first guy. But for from the second sign onwards, you will have two choices. Either you can keep it or you can remove it. Now what you want to do is, for now, let's imagine that you don't remove and you just keep. Then how would you, like, what thing that do we need to calculate? We do need to calculate the minimum time required to travel, right? So since we want to find out the minimum time required to travel, for now, let's just focus on calculating the time required to travel. Let's not apply any operations. So in that case, what will happen is, when you are at the sign one, first sign, you would just say that, hey, I will travel um this distance between, when you are at the sign I, है ना? I'm talking about when you are at sign A, right? For each sign I, the time you will require to go from position I to position I plus 1 would be position I plus 1 minus position I. That is the distance between the current sign and the next sign. For this distance, you will travel every kilometer in time I amount of time. So this is gonna be the time required to travel from sign I to sign I plus 1, right? So whatever answer we have, that is the total time required. It would be incremented by position I plus 1 minus position I into time I, right? So this is gonna happen if you keep the sign also, right? Now let's figure out um, what will happen in case if we remove a sign. How would the um, time taken change? So when you decide to remove a sign, let's say for this sign you decided that, hey, I will remove it. So in that case, if you had kept it, then you would have traveled this much distance with the time I amount of time. If the time I for this guy was 7, then and the distance was 10, then you would have spent 70 minutes here. But now what will happen is, for this distance, that is um, position of 2 minus 1, we will actually spend um, time 0 amount of time for every kilometer if you remove it, if you remove the sign. Because if you remove the sign, then in that case, um, for this sign itself, you should have actually calculated this whole distance, right? So one thing is, if let's say you are thinking about moving from right to left or something, deciding for every um, sign whether you would remove it or not, in that case you can directly calculate the whole distance in one go. But you would not really know how much this thing would be, like how much uh, time would be for the current sign, because if you remove some other sign, then the time can change. Like there are some complications which you do expect from a hard problem. If everything had been so easy, then obviously this problem would not have been considered as a hard problem, and even the submissions for the problem were very low during the contest. So we have seen, if you keep it, then this is going to be the time required to travel. If you remove it, then the time required for this range would be this. Oh, why is this city coming out? Okay. So in a nutshell, what we can do is, in the recursive function, let's say the recursive function is with name solve. One thing that we can keep track is the index I, that is the sign that we are talking about. Next thing that we can keep track of is the last unremoved sign. So if you remove the sign in the middle, don't count it. Just keep track of the last sign that has not been removed. Because if you decide to remove this current sign, then the time required to travel from sign I to sign I plus 1 will actually depend upon time last. Right, right. We have realized this thing earlier, that if you remove this guy, then the last sign that has not been removed would actually be important for us to find out the time required to travel from here to till the next sign. So we do need to keep track of the last sign that we have. Another thing that we need to keep track of is the um, number of signs that we have already removed, right? You do need to know about the number of signs you have removed, because at the end of the day, you want this thing to be exactly equal to k. So guys, is it making sense? Like we can have this kind of an approach for the brute force solution, for the recursive solution. We are not applying any DP right now. We are just thinking about the brute force solution or the recursive solution, which eventually we will optimize using DP, right? Is it making some sense? Bro, I also think about DP approach, but it not work. Yeah, it makes some sense. Okay, nice. Though there is one major flaw in this approach right now, the flaw is, let's say if these were the signs, I removed the first sign, I took the second sign, I removed the third one, and this fourth is actually the current value of I. This is the value of last for now, and the count removed is equal to 2. Now, for the this guy, if I decide to remove it, then the time required to travel in this range, according to our approach that we have discussed so far, or the approach that we have created so far, the time required should be time of last multiplied with position of I plus 1 minus position of I. है ना? It looks intuitive, but the problem here is, since we had removed this guy, the value of time last should have been updated, right? And um, like you don't really want to make any changes to the original array you have. You only want to make changes in the parameters or keep some information in the parameters, because at the end of the day, you would be considering all of the possible combinations. So if I update the value of time last for now, um, later on, either I will have to reset it in some way or something. But basically, the main idea is, if I update the value of time last, or if I just make any changes in the time array directly, then I would never be able to apply DP or anything. है ना? In any problem, you can never apply DP if you're altering the original array, right? So since we know when we will eventually have to use DP, we would have to apply some. You would have to apply or keep some information regarding this in some parameter or something. We can't change the original array. So for dealing with this, it's pretty simple. You can have a variable, let's say int last time. Basically, this last guy is giving you the index of the last sign that has not been removed so far, the last sign that you had kept. And this last time is telling you about the time of the last guy, the time that you had to use. And similarly, if you decide to keep this current guy for the case if you remove it. So like the thing that we have realized is, in the parameters we did know, like in the parameters we did need to have another parameter, let's say last time. And yeah, here the thing is, if you think about remove I. If you think about removing the current guy after applying the operation, then the time you will require for this range would be position of I minus I plus 1 minus position of I multiplied with last time instead of time last. Okay? We will not use time last because it can have some problems. In the case, like if time last is actually updated because of some reason, we will use another variable last time, in which we will keep track of the um, sum of all of the signs before the last guy also that have been removed. And for the other operation, that is keep, for this transition, the time required should be position of I plus 1 minus position of I. No, this is actually wrong. We have discussed this. Um, I told you about this because it did look more intuitive, but um, it had a flaw which we have covered. Similarly, for the current guy, if you intend to pick up, if you intend to keep this sign, then the time required would not be position of I plus 1 minus position I multiplied with time of I. In reality, it would be the sum of time of I for all of this. It would be summation of time of j for j from last plus 1 till I. है ना? Basically, the uh, from the last plus 1 sign onwards till the current sign. So in case if you had no sign that has been removed in the middle, then the summation would be just equal to time I. Otherwise, summation would be equal to time I, like this whole thing. Guys, does it make sense? Does it make sense? I know it might be looking a little complicated, especially if you have never got into some trouble. Like, you know, when you um, when you have never got a wrong answer and you have never spent hours debugging this kind of a mistake, um, it won't really look natural. So if it does not look natural, if it does not make much sense, then apply any transition which makes sense to you right now and get the problem. Spend hours debugging it. And at the end of the day, you do know the transition which will work. So it will help you to debug or realize the mistake. So it will make more sense in that case. So in a nutshell, what I want to say is this part of why we actually are using one more parameter and why the things have changed like this. If it does not make much sense, then don't worry about it. Just code it with any transition which is making sense to you right now. है ना? It may be wrong, but what is the worst that can happen? You will get wrong answer on the sample test cases. And then while debugging, you will realize the mistake and you do have the correct solution. So you would not have to spend a complete day at debugging it, which is good. So in a nutshell, what we have realized so far is we can have these four parameters with help of which we would actually be able to make we would actually be able to make decisions of what would be the time required for this much portion if we remove the sign or if we keep the sign. In case when you remove the sign, please make sure that you increment the value of count removed. You increment the value of this count removed variable. When you keep it same, you don't have to increment it. And in both of the cases, I should be incremented. And in case if you keep in the case when you keep the current sign, the value of last should be updated to I, right? So this would be incremented in both the cases. Last would be updated if you keep the current sign, because for the signs that will appear in the future, the current sign will act as the last sign for them. The count of removed will be increased if you apply the remove operation, if you remove the current sign by using the merge operation. And the value of last time, in case if you keep sorry, in case if you remove the current sign, then in that case, the value of last time will remain the same because the last guy is still the same for him. And if you decide to keep the current sign, then the value of last sign should actually become equal to this. Right. So you will store the value of this thing in the value of last sign, and then you will multiply. Right. Now, one doubt you might have is that for calculating it, we would have to use a for loop. So yeah, you can use a for loop, but a better way, since we would have to do this thing lots of times, we can use a prefix sum array here. I'm not sure if um, using a for loop would be okay or not. It might be okay, it might not be okay. Depends upon how many iterations we are having. But using prefix sum array will definitely work because uh, it will be able to do this job in big O of one time. Okay, so for converting the solution into a DP solution, all we need to do is just use the memoization technique to um, do some sort of a cache. You know? So all the parameters that we had, basically all the variables that we had, would now be stored inside the DP states. DPI last count of removed, and the last thing is last time. Right. This DP state will store the minimum travel time till the position of I, because if you are at this sign, then you have already traveled this whole portion, right? So you have already traveled from 0 to position of I. So minimum travel time till the position I, or the ith sign, um, such that we have removed count remove number of signs. We have removed this many signs, and we are keeping track of last sign that the last sign that we had kept, we had not removed, and the updated time of the last sign. Right. This last time is actually denoting the updated time of the last sign that you kept. Because whenever you remove a sign, the time for the whenever you remove a sign, the time required for the next time would be updated. It would increase, and we did not want to make any changes to the original time array that we have, because if you make changes to the original time array, that is something you cannot actually store inside a DP array. है ना? And everything that is not static, that is changing with the operations that we have, or basically which is not independent with the state, should be kept inside the state. This is actually one of the basic principles of TP. So to make sure that we don't break it, we would store the last time here. And in case if you did not understand the real point behind having this dimension, then the thing that I would recommend you to just ignore it and try to solve the problem yourself. You will make some mistake, and you will struggle right now. Like, the more you struggle right now, the better it would be. Because right now, if you don't understand this thing and you just accepted it as a fact that, hey, if, uh, the editorialist is saying that include this in the state and you do include it by listening to me, then when you get this kind of a problem, when you make this kind of a mistake in a real contest, you would not be able to debug it on your own. So if you make the mistake right now on your own and you try to debug it, you would actually find out a way of debugging your mistake, so that once you make this same mistake in a contest, you would be able to um, debug it that time also. Okay, let me show you the transition also. Like this is the state that we have made. The base case is simple. For the first cell, we have only one choice. So either you can, like what you can do is just say dp10 count removed is 0 and the last time would be equal to times u. You can set this thing to 0. This can be your base case. Sorry, not 0, but you can set this thing to be um, position of 1 minus position of 0 multiplied with time 0. Yep. This would be your base case. Your final answer would be dp of n minus 1. The last guy can be anything. The number of people that you would have removed, the number of signs that you removed should be k, and the last sum can be anything. So basically, you can run two for loops, one for this dimension, one for this dimension, and check out all of the states, all of the possible states where these two things are fixed. And whatever is the maximum, whatever is the minimum answer you get, that would be your final answer. So last, and we will just find out the minimum, where last would be in the range from 0 to less than n minus 1, or yeah, less than n minus 1, and last time would be in the range from 0 to 100. Right, so you will have these two for loops. Nextly, talking about transitions, if you are at a state dpi last count removed, for now I will just call it as rem count removed, and the last time, if you are at this transition, for the case where you don't change anything, like you keep the current time, current sign, then the state that you will reach is dpi plus 1. Last would be equal to I. The number of signs you have removed would be kept the same, and the last time would now be equal to the summation of j from um, previous last plus 1 till I. Um, right. This would be the state you would have reached, and um, that time you would have spent for reaching to the next cell, the next sign in that case is something we have already written. It would be like this thing: the distance traveled and the time per distance. You know, and for the case where you remove, you would go to the next. You will reach the next cell. Sorry, next sign. The last sign will remain the same because the current sign is removed. The number of signs you have removed will increase by 1. Um, by the way, for keeping your solution optimized, you can put up a limit that, hey, in case if the value of rem is less than k, then only in that case apply the remove operation. Because if the value of rem is already equal to k or greater than k, then in that case, applying the transition is not really gonna affect your answer. It will just make your code a little slower because of the redundant work that we have been doing. Nextly, the value of last time will remain the same. So this would be the state you will reach in case of removal. This is the state you will reach in case of keeping the current sign. That's it. So do you guys have any doubts? We can pre-compute. I think you're talking about the prefix summary that we had discussed here. Yep, it has. I'm getting something, but I think I have to code it up once on us. Yep, you need to code it on your own. You see, what happened? Though it doesn't really matter much. Okay, the code should have. Yep, yeah. So um, here is a small disclaimer. My my code will probably look complicated to most of you, especially if you are not very comfortable with iterative DP. The code I've written here is actually um, written with push DP. The iterative code with push DP. This is actually a lot better than the normal code that is being taught to beginners in DP sessions. Generally, you will see people teaching you the way to write a brute force code, then do the memoization part, like the way that we have done so far in the session. We have not really written the code, but we have discussed the brute force solution first, then the memoization part, and then uh, people will teach you to go to the iterative code, and then they will teach you how to space optimize it. But for competitive programming, if you go in this way, your code, like your speed would actually be pretty bad. Hana? And there are too many problems which you cannot solve with pull DP. There are two ways of applying DP. One of them is pull DP and the other one is push DP. Let me give you an overview here. So you do know you create DP states, right? You create DP states um, as we have created this state. So one way for thinking about transitions is in a way that you have a state and you go to some other state. This is push DP. You do think from the perspective, like from for the current state, you do think in the perspective of going further. Like from this state, where can you go? And this is most of the times very intuitive. The other case is pull DP, in which what you do is you think from the current state's perspective. You know, this was the current state. So here, this is your current state, and you actually in push DP you were thinking where can you go. In pull DP you think from where can I come to the current state, right? So whenever you write the recursive code, it is gonna be in pull DP only. You can, I think you cannot write a push DP code via recursion. At least that is something I heard once, and I've never really tried to write it in recursive. Okay? Whereas if you write an iterative code, you can write it in both ways. You can write it in push DP and pull DP. So this is something I would recommend you. Practice writing push DP code directly iteratively. है ना? Writing iterative code is very simple when you think from the push DP perspective, because thinking about states is also simple. You think about a state, so thinking of from which states can I reach this state is generally more difficult, and a lot of times it is not even possible, because if you are having some bitwise operation like um, and operation or something, then in those cases you can't even figure out the states from where you can come to this position, and you will have to actually check out way too many states for this. Whereas in PushDB, you can precisely figure out the states which you can reach from here. So this is gonna be more optimized. Nextly, this is iterative, so obviously this is faster. And the way, like I will show you my code, the way I write iterative DP is also very simple once you know how it is working. Um, right now, if you are not comfortable with iterative DP and you go in this way, then it might look complicated, but that is where you are learning. If I look at some grandmaster's code, I also feel it to be complicated. But when I spend a lot of time at understanding how things are working there, if I look at Jiang Li's or tourist sport, that is where I learn some new cool way to write code. Write a shorter code or a cleaner code or a more flexible code, right? So here you can also learn about it. So the main logic here is we wanted to apply DP. So the first thing that you would definitely do is just create the DP state. So um, yeah, the syntax might look a little unnatural. Generally, we write like this. And you can see how cluttered it will become if I have to create a 3D DP like this or a 4D DP. Right now, we have to create a 4D DP. So how cluttered it will become, right? There is another syntax for creating vectors that is just write vector and then whatever the name is, and then the size of the first dimension, then again vector, and just keep on doing it. So this will keep your code a little less cluttered. Obviously, it's not as clean as we have in case of arrays. Arrays are super clean when we create them. Right. It's not gonna be as clean as arrays. Whatever. At the end of the day, we have created the DP state as we wanted to create earlier. Yeah, we actually forgot. I actually forgot about one thing. The DP state that we created there was DPI last number of people to be removed and last thing. Right. So there will be n possible values of I, n possible values of last, k possible values of number of elements that have been removed. In place of rem, you could have actually kept track of the number of signs that you have not removed. But the problem is the number of cells that you will remove would at most be 50, would at most be 10, whereas the number of cells, the number of signs that you would not remove can at most be 50 or 49, something like that. So keeping this part is actually better for us. We will have less number of states. And for the value of last sum, it can never be greater than 100 because the sum of the values of time I, like sum of time I is actually less than equal to 100. This is being given in the constraints. So 50 into 50 into 10 into 100. So it will become 25 E4, sorry, 25 E5, which is somewhere like 2 E6. So right now, I think even if we had created a worse state where we are keeping track of the number of signs that we have not removed, then also the number of states would be somewhere like 1E7, which is still gonna work, but you might need space optimization there, and will become a little slower. And this is like the current approach is still gonna work for sure. 2E6 is actually a very good time complexity if it's actually 2E6. Yep, it should be 2E6. Okay. Um, the base case as we had discussed. Then, yeah. So now for the part of transitions. Whenever I write iterative code directly, the way I write it is on my iPad or earlier when I used to use notebook. You have to first of all think about the state. Let me just show everything that I had mentioned here. While thinking about the logic part, you have to think about the state, the base case, the result, and the transitions. At least these four things are always going to be used. Um, and most of the times, I think these are the only things you will need. So you think about the base, you think about the state, and you know what thing you want to calculate. If you want to find out the minimum of something, then you initialize everything with the maximum possible, like a value even greater than the maximum possible value you will ever have. So something that will help you to figure out whether the state is reachable or not. like in any case, the answer for any state will never be greater than 1e7 because the distance, the length of the total road is just 1e5, and that time, sum of time is just 100. So in any case, you can never have um, total time required greater than 1e7. So I initialized it with something bigger and only fix the base case or base cases if you have multiple base cases sometimes. Then for the transition stuff, first thing that I do is I just write four for loops or three or two, whatever's the number of dimensions I have. Right now I have 4 dimensions. So I have written 4 for loops. Every for loop is denoting the dimension I have. Right. Now there is one more thing you need to remember while writing these um, for loops. That is, look at the transition. Right now in our transition, dpi, like this, I is smaller than I plus 1 and I plus 1. So like you just want to make sure that if there is any state, like for every state, to whichever states you can go, and you have created these transitions. So this state should be calculated completely before these two, right? So like it is generally not difficult. In case if it becomes too complicated, then we do go with the recursive DP in those cases because it can it can save us a lot of time sometimes. But in general, this is not too difficult. You can see that DP of I or whatever we have here has to be calculated before these two, right? So if you just have the for loop of I outermost at the outermost position, then until all of these for all of these variables, basically until dpi, and these three can be anything, all of them have been calculated, you will not go to any of them, right? So uh, I think I can't explain this more. um, this is looking like a very simple thing. uh, just to give you a simple example here, if you see, for calculating Fibonacci of 5, you do need to know about Fibonacci of 4 and Fibonacci of 3, right? When you used to port the DP solution with memoization or recursion, you used to call recursion for these. है ना? So what used to happen was f of 4 and f of 3 used to be calculated first, and only then f of 5 was being updated. You want to do the same thing here also. And uh, if you have learned about DP from any resource, probably you would have seen someone converting recursive DP to iterative DP. So the person must have mentioned at that place also that for every transition, just make sure that this state which you are using for calculating some other state is being calculated before the other state. And right after the 3 or 4 or 2 for loops I have for going to every state, I write one line here, that is, if the current state is having the value equal to np. Np is basically um, just the short form of not possible. This is just a name that I write myself, not a standard thing. So you can just have this if condition here to make sure that if the current state is not reachable, then just continue. Because if you can't reach the current state, then obviously you can't go beyond it. है ना? If I can't even reach to this state, then how can I contribute from this state to this state? Obviously I cannot. So just continue. Right? Nextly, I am doing the transition part. So I did not want to write position I plus 1 more than once. So I created a variable dist for it. And here time sum is basically the summation part that we had here. Yeah, time sum is this part, the summation. So to calculate this thing efficiently every time, I went up and created the prefix sum array. And yeah, by the way, for the DP state, here you could have actually created the last state with size 101, but I intended to create it with total sum plus 1 because it would be a little faster. है ना? Like negligibly faster maybe. Um, okay, so I have got time sum also. Now I just have to write the two states. So generally, when I have more than one state, what I do is I write the logic for the transition for each transition inside a different scope so that I can create some variables if I need to, which are to be used only for the current transition. For this as well, I had initially written this thing inside um, scope block, but before the PCD, I removed the block so that the code looks more neat. It looks neater. And for the second case, I do have an if condition here that the number of signs that I've already removed should be less than k so that I can remove the current sign also. Here is the current transition. Now the transitions may look very long because the DP states we have are very big since we are having four dimensions. But the logic part is very simple. This is the state that we will reach. We had written it here also. You know, everything that I do in the code part is always written in the uh, like the place where I'm writing stuff for maybe it's a notebook or an iPad or whatever. I do write it first so that in case if I'm about to make some mistake, like if I make some mistake while thinking about the logic here in the iPad, then I'm more likely to be able to see it. Whereas if I write this while writing the code and I make some mistake, then it would be even more difficult to debug. So here we had um, this as the state, like this as the um, state that we will reach if we keep the element. So you see DPI, this is removal maybe. Oh, sorry, yeah. Yeah, DPI plus 1, I, rem, and time sum. That is the exact same thing. Similarly, another DP state, DPI plus 1, last, rem plus 1, last sum. This is the exact same thing. So if you just write this thing in a notebook once, then you would be able to write your code with very less chances of making some mistake in comparison to if you directly write the code when you're thinking about the logic or if you are not completely sure about the full logic. As for the transition, this is the cost for reaching till the position I, and we will like this will keep track of the cost to reach till the position I plus 1. So you want to find out what would be the cost to reach here, like from position I to position I plus 1, and that would be equal to the distance that you have to travel and the time sum that would be the time required for every kilometer. Similarly, the same logic goes here. Then at the end of the day, you have to find out the minimum of DP, like you have to find out the minimum possible travel time such that you are able to reach to position n minus 1. You have to reach there and you have to make sure that the count of removed guys is equal to k. There are only these two constraints, and in a DP state, we are having four variables. That is I, last, count rem, and last sum, like last sum or last time, whatever you say. So here I should be equal to n minus 1, and count rem should be equal to k, right? For the other two dimensions, they are variables. So we will just run two for loops for them, check out for all the possible values they are giving, and find out the minimum possible answer there, and we will just return it. So I think the explanation for the C problem might have been a little too big, but I did not just tell you about the solution. I actually explained you the way in which I do solve problems related to DP. And I believe for most of the viewers, this would be something they don't know. Um, like, I think there can be some people who know about this as well. Um, when I got to know about this thing while watching Amnik's PCD, or not PCD, but his screencast, I saw him just writing iterative code directly. And I saw it was a really good way. And when I started using PushDP after watching it actually helped me a lot. Like earlier, if I used to get 10 problems of DP, maybe I could solve only 3, 4 or so. But after knowing about it for the similar difficulty problems, it was like I could solve all of them during the contest. Okay, so we have discussed the time complexity as well. Maybe we can end the stream now. Let me look at the comments. Nice explanation. Thanks. Resources for this push TP. I don't know. Like to be honest, I had not learned about push DP from some resource. I just saw someone writing iterative code directly, this kind of a code. And once I saw him write this kind of a code, I just realized that hey, this is really cool thing. Instead of calculating DPI last rem that I used to do earlier, after I saw him, I realized that hey, I can use this current state to actually update the states where we can reach. And later on, I got to know that this is actually a standard, or not a very standard technique, but a well-known technique. And it is known by the name push DP. By the way, this push DP is being taught in TLE Eliminators as well. Um, about this thing as well, I got to know about it when I joined TLE Eliminators, or maybe I don't know. Like after joining TLE Eliminators, I got to know about it. From Apna college channel, you can learn Java. Java DSC resources बता रहे थे. Oh, sorry. Um, yeah, I don't know about Java, and I think I had replied about this thing earlier also when someone was asking me about Java resources, and I told them that I don't know about Java resources because I have never really studied about Java. Guidance on practice. Yeah, I will look at your comment. Though Java I know, but Java DSA I want. Um, yeah, you can just if you know want to know about the pre-built data structures in Java, you can maybe look at Geeks for Geeks. They have resources for almost all the common things we need. Can you make videos like this TP problem explaining push TP ideas? Um, I don't know about TLE Eliminators channel, but I will do consider to upload it on my personal channel in future, but not really recently. Maybe after a few days or so. Okay, let me look at the previous comment. I have a question. Please guide me. If you have 6 months in CP, then how much practice will be your daily target and you have whole day to invest? How much time you will invest? This looks really promising. So if I'm gonna be really dedicated for DP, sorry, not DP, but CP for the next 6 months, and I can spend the whole day, then one thing I would do for sure is give all of the contests and give all of them like really honestly. Like if there is a contest of code forces from 8 to 10, I will spend all of my time from 8 to 10 while thinking about the next problem. Like I let's say solve A and B, and I'm very rarely able to solve the C problem. I will not give up after 15 or 20 minutes. I will actually spend I will actually try the C problem till the end of the contest. If I am actually um, willing to grind for CP. Nextly, for the part of practicing, when you solve problems in the contest, you will um, like many times when you are not able to solve a problem, let's say you solved A and B but could not solve C, and then you looked at the solution, you will actually see the topics that were being used for solving the problem. When you see a topic coming repeatedly, then in that case you can just go to practice problems for the specific problem tag of that specific topic. Maybe like if you're um, again and again failing to solve the C problem for by which could be solved using binary search, then maybe just go to the problem set and filter all the problems of binary search with some problem difficulty range and then practice them so that you will start um, realizing some patterns which come in binary search. Like there is um, apart from just the patterns which you will realize in the problems, you will actually develop your what do we say? Basically, muscle memory for coding problems using binary search. Like if I get a problem, which if I ever have to apply binary search in a problem, I'm I don't have to think much about the variables that I would create or so. There are a lot of things that would just stay constant for all the problems. If I have an editor, maybe I can show. Yeah, so let's say if I have to apply binary search here for something, then the first thing I would do is I will just create two variables s and d. Let's say initialize them with something. I will just think about the range in which my answer should come. If I have to maximize my answer, I always initialize the result with s. If I have to minimize my answer, I initialize the result with e. And while initializing it, I do think about one more thing. Will my answer be always true for S or E? Like would whatever condition I am about to apply, would it always be true for S or E? If it is always true for S, only then I will initialize the answer with S. Otherwise, I will initialize my answer with -1 or something, so that at the end of the day, I will be able to figure out if I did not get the condition satisfied for anything. Then I always have this S less than equal to E stuff and M equal to S plus E by 2. And then if check M result equal to M and S equal to M plus 1 and in the else case equal to M minus 1. And then at this place I will have my answer that I wanted in the value of risk. And I do create this check function here. And I do write my logic for whatever condition I have inside this check function, which will return either yes, like either true or false. And this makes sure that I have a very short code. Whatever S and E stuff I have, in case if binary search is the only thing I have to do in the function wherever I have been writing this code, then I will just declare them straight away. Otherwise, if I'm having a, let's say, big block of code and inside this for something to find I'm applying the binary search, then what I will do is I will initialize the result thing that I need to find outside the scope block. Then I will create the scope block. And inside this, I will write the stuff. So whatever things I created inside this scope block would not really affect my code at any place. And I would have just found the thing that I wanted to search for. If I have to apply multiple binary searches, then I sometimes might um, create a lambda function inside which I pass on some lambda functions and whatnot. Bro, today I did only one problem. So if you did only one problem, then and you know about recursion, then please absolve the B problem. And for absolving it, please don't look at my code. Just solve it yourself. Spend at least a lot of time, like until you just don't have any motivation left to try the problem yourself anymore. And once you are at that position when you don't want to do it yourself anymore, only then look at my code for debugging it. Yes, you replied in. Bro, today I did only one problem. You replied in. Thanks. Yeah, so that's great. And shall we end the stream then? I think we have discussed everything that we had to discuss. Yeah, so let's bye. Goodbye.